Okay, today we're doing the last lesson of the logarithms unit, looking at graphing logarithmic functions. So you should recognize the graph of this function here in blue. It has a horizontal asymptote of y equals 0. The points 0, 1, and 1, 2. Right here. That is the graph of the exponential function y equals 2 to the x, right? Because 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, etc. And we can see that it's in the shape of an exponential function, and the fact that it has a horizontal asymptote at y equals 0, we know that there hasn't been any vertical shift. Okay, if we reflect this function over the y equals x line, we're finding the inverse of that function. And the inverse of that function happens to be log base 2 of x. If you weren't familiar with that, you could figure that out. If we have y equals 2 to the x and we wanted to find the inverse, remember we're switching x and y. Okay, so the inverse, we can switch x and y and we can then solve for y, right? So if we want to solve for y, we can rewrite this function in logarithmic form. So we've got log base 2 of x equals y. So log base 2 of x is the inverse of y equals 2 to the x, which means when we graph this, it's going to be a reflection over the y equals x line. Okay, so graphing logarithmic functions. Remember, with logarithms, we can't have a negative base, and this number here, our x in this case, cannot be negative. So it's maybe easiest to look at when y equals -2, -1, 0, 1, and 2, and then try and figure out what x is. Thinking 2 to the power of -2 is equal to what? There we go. Okay, so this is actually y. Okay, so 2 to the -2 is equal to what? Well, that's 1/4. So this is actually backwards. Here we have y and here we have x. So we've got the point 1/4, comma, -2. Okay, here we're thinking 2 to the -1 is equal to what? X value. So 2 to the -1 equals 1/2. Okay, 2 to the power of 0 is equal to 1. So we've got the point 1, 0. Okay, here we've got 1. So just to clarify, we're saying log base 2 of x equals 1. Okay, so we've got 2 to the 1 equals x, which means x equals 2. So x equals 2, y equals 1. Okay. In this next one, we've got log base 2 of x equals 2. So we're thinking 2 squared equals x, which means x equals 4. Starting with x's here, and then these are our y's over here. Okay, so we've got the point 1/4, comma, -2. We've got the point 1/2, comma, -1. We've got 0, 1. We've got 2, 1. And we've got 4, 2. This is the graph of y equals log base 2 of x. So it's a reflection over the y equals x line. Okay, we can see that. We could have also, right from the start, just switched the x and y values. So this is the point 0, 1. When we do the inverse, we have the point 1, 0. Okay, we've got the point 1, 2. When we do the inverse, we've got the point 2, 1. Okay, and etc. This is 2, 4. This is 4, 2. And notice that our horizontal asymptote at y equals 0, right here, became a vertical asymptote at x equals 0. Okay, so with logarithmic functions, we're dealing with a vertical asymptote instead of a horizontal one. Also think about the domain of our function. Remember x, this value here, cannot be negative, right? We can't take log base 2 of some negative number. We can't have 2 to a power to give us a negative number. So it makes sense that our function wouldn't go past x equals 0. And in fact, x never does equal 0. We can't have x equal to 0 either, because we can't have 2 to some power equal to 0. Okay, it just doesn't work. There's no way that we can have 2 raised to a power to give us 0. Okay, so that is log base 2 of x. Here we're looking at log base 3 of x. We can see we've got, if we do log base 3 of when x equals 1, so this is log base 3 of 1 is equal to y, right? And 3 to, so we're in our head, we're thinking 3 to what power equals 1? Well, of course, y is going to be 0. So we have the point 0, comma 1. So log base 3 of 1, log base of any base of 1 is equal to 0, right? We've also got the point 3, comma 1, because if we do log base 3 of 3, we get 1. Okay, log base 3 of 9 is going to give us 2, so we would eventually have the point 9, comma 2, etc. Okay, so we've got our log base 3 of x graph. Notice again we have a vertical asymptote at y equals 0. We want to drag this red star here 1 unit down and 2 units to the right. So 1 unit down and 1, 2 units to the right. And we've got this new transformed function. Okay, so what is the translated graph? Well, we've got log base 3 of x originally, right? We moved our function 2 units to the right, so it's going to be x minus 2, and we moved it 1 down, so minus 1. And we can see that our vertical asymptote moved 2 to the right as well. And we can see that the point 0, comma 1 moved 2 to the right and 1 down to make it 2, shoot, I said this backwards. Okay, my mistake. This is originally 1, comma 0. Okay, and this is 3, comma 1. Okay, so the point 1, comma 0, there we go, has moved down 1. So it has a y value of negative 1, and it's moved over 2. So that's 3, comma negative 1. Okay, so what is the x-intercept? So originally, we had the x-intercept 1, 0 on our original function, and now it's at 5, 0. Okay, so the x-intercept is 5, 0, and the vertical asymptote, instead of being x equals 0, it's now x equals 2, because our entire function shifted 2 to the right. Okay, so here we want to think about how is the graph f of x equals log base 2 of x, which is the one in blue here. We've got the point 1, 0, and we've got the point 2, 1. So we're thinking, okay, log base 2 of 1 is equal to 0. That's true. Here, this is the point log base 2 of 2 equals 1, which is also true. Here we've got the point 4, comma 2, which is log base 2 of 4. So 2 to what power gives us 4? And of course that 2. Okay. And we want to figure out what's the transformation that then creates this red graph. So we can see it's a reflection over the x-axis, right here. So to do a reflection over the x-axis, we'll simply make our function the opposite, right? So we'll need negative f of x, which means our function will be negative log base 2 of x, okay? And we can see that that works. So if originally we have the point 1 comma 0, we're just going to make y negative, right? And then we get the point still 1 comma 0, which they both share. Here we've got the point 2 comma 1. We're just making the y negative, so we're just making 1 negative. And then in the reflection, the graph of the reflection, we have the point 2 comma negative 1, right? We want to write it in two different ways, though. So, of course, we've got y equals negative log base 2 of x. We can also write this. We can think of this as negative 1 times log base 2 of x, right? So remember, this is a coefficient of a logarithm. We can put our coefficient up as a power. So we get y equals log base 2 of negative x to the negative 1. Okay, so we've written it in one way. This is a second way we can write it. Or we can simplify that x to the negative 1 as y equals log base 2 of 1 over x, which is the same as x to the negative 1. So three ways that we can write the exact same function. So that's all three of those ways show this red function that's been reflected over the x-axis. Okay, here we want to write the equation of the graph. Okay, so we're given a graph. We can tell that it's a logarithmic equation because of its shape. We can see that it has a vertical asymptote, whereas an exponential function has a horizontal asymptote. Right, so right away we can tell that our logarithmic function has been moved 2 to the left. So we know we're going to have log of some base, we'll call that b, of x plus 2. It's moved 2 to the left. Okay, originally, if you look at log base 2 of x, okay, this red graph here, we've got the point 1 comma 0 and 2 comma 1. So it's important to try and figure out on your transformed function, where did that 1 comma 0 point go? Here's 1 comma 0. This has been moved down 1 and left 2. So that's minus 1 here. So we want to figure out our base here. We've got the point, on our graph, we've got the point 2 comma 0. Okay, so we can plug in x equals 2 and y equals 0 to find our base. So y equals 0, x equals 2. We've got this minus 1 because our graph shifted down 1. So we've got 0 is equal to log base b of 4 minus 1. So 1 equals log base b of 4. And, oops, log base b. And we can rewrite this in exponential form then. So we've got b to the power of 1 is equal to 4, which means our base is 4. Okay, so our whole equation is log base 4 of x plus 2 minus 1 is equal to y. And we can check that just visually that makes sense. We can see, yeah, we can just plug that point in again. We can say, okay, log base 4 of, here we've got the point negative 1 comma negative 1, right? So log base 4 of negative 1 plus 2 Negative 1 plus 2 gives us 1. Log base 4 of 1 is 0 because we're thinking 4 to what power gives me 1, not 0. 0 minus 1 gives us negative 1, which is the y that we're looking for. We could also try the same again with the same point that we used just to check. Okay, so here we're given the graph of a function, and we want to graph its inverse, and we want to find the equation of both functions. So hopefully right away you can recognize that the blue function is an exponential function. We can see it has a horizontal asymptote at y equals 0, and we can see we've got the point negative 1, 1, and 3, 0 here. Okay, remember with exponential functions, if we want to write the equation of this function, we can see because it has a horizontal axis of y equals 0, that it hasn't moved, it hasn't shifted vertically, it hasn't moved up or down. So if we write y equals a times b to the x, we know that the vertical shift is 0, okay, because of the horizontal asymptote. Okay, then it's nice to use the point 3 comma 0 to try and determine our a value here. So if y equals, this isn't 3, 0. Oh my goodness, I keep making this mistake. Okay, 0, comma 3. So we're going to use that point. So our y value here is 3. A times b to the 0. B to the 0, of course, is 1, so a has to equal 3. Okay? Now we need to find b. So we can use our last remaining point. Did I do that one right? Negative 1 and 1. Okay. So we'll have y is 1. We know a is 3. We're trying to find b, and b is going to be to the power of negative 1. Okay, so we'll divide both sides by 3. And we'll get 1/3. So 1/3 equals b to the negative 1. B to the negative 1 is the same as 1 over b. And here we can cross multiply, or we can think, okay, if we have 1/3, b has to equal 3. Or we can say, okay, b times 1 is equal to 3 times 1, or b equals 3. Okay, so our final equation of our exponential equation here is y equals, our a was 3, our b was also 3, to the power of x. We can simplify this. This first 3, our a is 3 to the power of 1. We can add our exponents because we have the same base. So we can also write this as 3 to the power of x plus 1. Okay, so y equals 3 times 3 to the x, or 3 to the x plus 1. 3 to the x plus 1 is the function 3 to the x, but shifted to the left one. We want to write the inverse of this function. It says that if we run this magnifying glass over the graph, we should be able to see it. So you can see the inverse here. And we can get that graphically by switching every x and y value. So here we have the point negative 1, 1. We can just switch those. So we'll have the point 1, negative 1. Here we have the point 0, 3. We'll switch those values, and we'll get 3, 0, and so on. And originally we had a horizontal asymptote, and now we're going to have a vertical asymptote at y equals 0. Or sorry, x equals 0. Okay, so we've got our logarithmic function. We want to be able to write the equation of this function. So we can simply just switch x and y. Okay, so if originally we had y equals 3 to the x plus 1, to find the inverse, we can switch x and y. So x equals 3 to the y plus 1. And then we can solve for y. So we can take the log, we can rewrite this in logarithmic form. So we can say we've got log base 3 of x equals y plus 1. And then y, to get it that alone, we'll have to minus 1 from both sides. So log base 3 of x minus 1 is equal to y. So this is the inverse of our function from before. So if we call our function before f of x equals 3 to the x plus 1, our inverse is going to be log base 3 of x minus 1. Okay. So the reason that makes sense is generally, if you think about log base 3 of 1, so log base 3 of 1 is equal to 0, right? Because 3 to the power of 0 is 1. So it would be this point here. If x is 1 and y is 0, we're talking about the point 1, 0. Log base 3 of 3 is equal to 1. Log base 3 of 3 is equal to 1 because 3 to the power of 1 equals 3. So that gives us an x of 3, a y of 1. So that's this point here. Notice, okay, that is the function log base 3 of x. And every point that we have has been shifted down 1. Okay, so we can see it has a vertical shift of -1. Okay, so we've got our original function, we've got our inverse function. Here we're just graphing logarithmic functions. And they have undergone some horizontal and vertical shifts. So let's start by thinking about log base 2 of x. Okay, just the original function, log base 2 of x. Okay, if we make x equal to 1, so if x equals 1, we've got log base 2 of 1, which hopefully you recognize log of any base of 1 is always going to be 0, because 2 to the power of 0 is equal to 1. Okay, or in your head you're thinking 2 to what power gives me 1? Well, of course, that's 0. Okay, so we have x at 1, y at 0. So 1 over 0 up. It's hard to read. Okay, log base 2 of 2, we should also know. Log base 2 of 2 is 1, because 2 to the power of 1 is equal to 2. So we have the point, our x is 2, our y is 1, so 2, 1. Log base 2 of 4. Notice they all have to be powers of 2. So log base 2 of 4 is equal to 2 because 2 to the power of 2 equals 4. So we've got x and y. So 4, 2. What else could we do? 8. Log base 2 of 8 is equal to 3 because 2 cubed equals 8. So that gives us an x of 8, a y of 3. So over 8 up 3. Okay, and then we know we should expect our logarithmic function to have a vertical asymptote at x equals 0 if it hasn't been transformed to the right or the left. Okay, but this function has been transformed to the right or left and also has a vertical shift. So x minus 1, that is a shift to the right. Remember, anytime it's in brackets, it's always the opposite of what we would expect. So every point is going to shift right 1. Okay, and then every point is going to shift up 2. That's just exactly what we expect outside of the bracket. So right 1 and up 2. So we're literally going to take every single point, we're going to move it right 1 and up 2. So if we start here, we're going right 1 and up 2. This next point, right 1, up 2. This point here, right 1, up 1, 2. And 8, 3 goes off the graph. And then we also need to move our vertical asymptote right 1. Okay, so instead of at x equals 0, we're at x equals positive 1. And this is our new function. Okay. All right. So again, here I would recommend graphing the original function log base 5 of x and then trying to picture your vertical and horizontal shifts. So log base 5 of x is going to be our original function. Okay, we can do log base 5 of 1. So in our heads, we're thinking 5 to what power? It's actually y. 5 to what power equals 1, and that power happens to be 0. So we've got x is 1, y is 0. So we have the point 1 comma 0. Log base 5 of 5 is going to equal 1, because 5 to the power of 1 equals 5. So we have an x of 5, a y of 1, so 5 over 1 up. Okay, and we know we've got our vertical asymptote at x equals 0. This graph is going to shift 1 to the left. Left because it's plus 1, that's really important, and 5 down because it's minus 5 outside of the brackets. Okay, so we're going to shift every point 1 to the left and 5 down. So originally we have the point 1, 0. We're going to shift it 1 to the left and 1, 2, 3, 4, 5 down. Okay, here we have the point 5, comma 1. We're going to shift that 1 to the left and 1, 2, 3, 4, 5 down. And our vertical asymptote, we're going to shift 1 to the left. Okay, so we've got our newly transformed logarithmic function. All right, thanks guys. Bye-bye.